Hello learners, welcome to Education Online program. In our previous lesson, we learned a lot about velocity time graph. So today we shall be looking at some examples, worked examples on the velocity time graph and then the distance time graph, so that we get to see how will you work out a number when it is given to you like that, or how would you draw a graph of a certain question. When the body is traveling, then they have described for you the whole motion in words. How would you put it in graphical form? So that is what we shall be looking at today. So let's have our example one. So our example one talks of a cyclist. So it's saying that a cyclist starts from rest and accelerates uniformly at 1 meters per square second for 20 seconds. Then he maintains the maximum speed reached for 1 minute and finally decelerates to rest uniformly for 10 seconds. The question is, draw a velocity against time graph for the body and then calculate the total distance traveled. Let me put the question down so that we try to summarize and see how we shall draw the velocity against time graph for the cyclist. So we have it as a cyclist starts from rest and accelerates uniformly at 1 meter per squared second for 20 seconds. Then he maintains the maximum speed reached for 1 minute and finally decelerates to rest uniformly for 20 seconds. Our question, Roman numeral 1, is telling us to draw a velocity against time graph for the body. Then after drawing our velocity time graph, we also have to calculate the total distance. The total distance covered by the cyclist. So we have it as our total distance covered. So now we have our question there. How shall we draw the velocity against time graph? So if you want to draw the velocity time graph, the first thing you have to see is that what are you drawing? What are you going to put against what? So you see that it's our velocity against time, which means that our velocity takes the y-axis and then the time will take the x-axis. Then again, something you have to check on your questions. What is the question telling you exactly? Was the body starting from rest, Or was it already given some other velocity for it to start moving? What is the time taken for the body to actually come to rest or to move from one point to another? So all those things you need to first find out in the question. And then the other thing is that you need to see, have they given you the time in seconds? Because we are saying that the standard unit for measuring time is seconds. So you can also find that they have given you probably in hours. But then if you have, like in our question, they have given you in minutes, what do? Then you have to convert the minute into seconds. Because if you look at your question, some time frame there has been given in seconds. You find others, there is also 1 minute. So there is a bit of minutes and seconds there. So you have to convert it to one, which is the standard unit, the seconds. So you'll see that how many seconds are there in 1 minute. So before you start drawing your velocity time graph, let us try to look at this now. They are saying that a cyclist starts from rest. So if it is starting from rest, what was the initial velocity of the body? So at rest, the initial velocity is 0. So they are saying it accelerates uniformly. In our previous lesson, we looked at the graph of velocity against time for a body moving with the uniform acceleration. How is the graph supposed to look like? So how is the line? How are you supposed to put the line in the graph? So here we are seeing that our body moves with the uniform acceleration. Then it moves for 20 seconds. So let us try to draw this velocity time graph. The first thing is we are going to have our y-axis, and then we shall have our x-axis. So if we have it like this, and then we have this here, this one is taking our time in seconds, and this is velocity in meters per second. They're saying that the body starts from rest. So this is the 0 point here, where this the y-axis, the velocity line meets with this one, with the time, is it is the 0 mark of the graph. That means that at this point here, velocity is 0, and also the time taken is 0 for the body. So meaning that at this point here, the body has not even moved. It is just at its same point. So here is where we shall start drawing our graph from. So we want, the first one is to show how the body accelerated uniformly. And we said when the body is accelerating uniformly, we shall have this line moving, straight line moving from the center here upwards. So this one is showing that this body has a uniform acceleration. Then what is it saying? It was moving with a uniform acceleration at 1 meters per second square. This is the value of acceleration for 20 seconds. That means that for the body to move from rest here up to that point there, it took the body 20 seconds to reach right there. So we shall demarcate, we shall pull our line down here to meet this time axis. So we shall have just the dotted, so that we are sure that it's on the same line. So at this point here, that means that the body had moved for 20 seconds. It started from 0. So what happens is that he maintains the maximum speed reached for 1 minute. How do you maintain a maximum speed reached? That means that the cyclist has attained a uniform velocity. And what happens with the uniform velocity? With the uniform velocity, the initial velocity and the final velocity the body will attain is what? They are the same. And then the acceleration there at that point is 0 for a body moving with a uniform velocity. So that means that this is where our body is moving. So we keep this line straight here, or a horizontal line here. This horizontal line will indicate to you that there is a uniform velocity right there, because if you check here, the velocity here, if you try to pull this together, you find that the value here is the same at this point and at that point. So if these two values of velocity are the same, that means that the body is moving with a uniform velocity. So now what happens to the cyclist after attaining the maximum speed for 1 minute? So what was the time frame for the cyclist to maintain a maximum or a steady velocity? They are saying that the cyclist moved with a uniform velocity for 1 full minute. But we are not going to write our 1 minute here, because we already have the first one here was already given to us in seconds. So what we do is we try to convert the 1 minute into seconds. So how many minutes are there in one? How many seconds are there in 1 minute? So you see that for the clock to read, assuming this is our clock, this is our minute hand. For this to reach here, it has to move. The second hand will move from here. It will continue moving like this, all circle up to here. That means it moves at 360 degrees, the whole of that. So when you try to count the demarcations in the clock hand here, what happens is that if you try to count everything here, you'll see that it counts up to 60. That means that if you have 1 minute, that means you can equate that to 60 seconds. So if you have your 1 minute as 60 seconds, what happens? Do you just take the 60 seconds and put it there? So let us see this. So this is from this point here up to this point is where the body was moving with a steady speed. Only this point here, because if you go up to here, if you try to pull it up to there, that means that you're going to cover this distance also, this distance, and then with this time frame, which is not the thing. So instead of you putting only 60 seconds here, that means that if you want to get the time the cyclist moved from this point to that point will not be 1 minute. If you just wrote it here as 60, to get this time here, you're going to get 60 minus 20. And what will happen? It will give you 40 seconds instead of 60 seconds. So you try to add the seconds, so that when you subtract this one in front of the seconds, in front of what you're writing here, so if you have this one, for you to get the exact 60 here, you need to add some figure that when you subtract this one, you will get 60. So which one could that be? What number could that be? You'll see that you can move from 60, if you have it as 70, and then subtract 20, you will get 50. So what if you have 80, and then you subtract 20? You'll see that you'll come back to your 60 seconds. So instead of writing 60 here, we write 80 seconds here at this point. So that when we try to subtract this from that, we make sure that we get the figure the time they gave us in the question. So when you have your 60, your 80, you subtract 20 from it, you see that the body moved from here up to there at a time interval of 60 seconds. So what happened again after the body attaining a steady speed? After that, maximum speed reached for 1 minute, and finally decelerates to rest uniformly for 10 seconds. So after this body moving with a steady constant speed, it then also come back, it was brought back to rest for 10 seconds. So we are going to bring our body back to rest. From here, we shall bring our body back to rest here. So it moves backwards in the opposite direction. And we are saying that it took the body 10 seconds to come back to rest. So you don't write just the 10 there, but then you add, so that when you get this number here and you subtract this number here, you will get the exact time the body came with to rest. So instead of us writing just 10, we shall write 90, because when you get 90 and then subtract 80 from it, you will get the 10 seconds. So this is how our velocity time graph will look like. You see that we have summarized the whole of this in just a simple graph. So it's the matter of you knowing the time taken for the body to move from one point to another, at what velocity. Was it uniform, was it non-uniform velocity? If you get to know that, then it becomes simple. So what do they want again from us? They want us to calculate the total distance covered by the body. We said for you to get the total distance covered by any body in a velocity time graph, you take the space, you try to calculate the space here. So this space here is the displacement, the distance covered by the body. So for you to get this, you can either use the equations of motion, or you can use any other formula that is suitable for that. For example, instead of using the equations of motion, you just divide your journey into stages like this. So if you have the stage, you know that this figure here gives us a triangle. A triangle, what you do is you can also use the area, finding the area of these figures. So because if you find the area of one figure and then you add all of them, you'll see that you still get the distance covered, this right space here. But for us for today, we are going to use the equations of motion. Let us try to see how we can get the total distance. So in our question, they are saying, we try now to summarize again the question. A cyclist starts from rest. That means that, let's give this one A, this stage here is B, and then this is C. We are taking stage A. What happens with stage A is, it started from rest. That means your initial velocity is equals to what? 0. So if our initial velocity is 0, what happened again? Then from rest and accelerates uniformly at this. So the acceleration the body used to move from this point up to there was given to us as 1. It is 1 meters per second squared. So if we have that, what again? It accelerates for 20 seconds. So we are having our time here for the body to move from 0 up to that point here as 20 seconds. So if you have it like that, how would you get the distance under that? Under this, only this first stage here, this stage A. So from your equation of motion, we are going to use our second equation, where we have this is equals to what? we have our ut plus a half at squared, because our s stands for distance, u is the initial velocity, then we have the acceleration and time. So if we have that, we can now get our s. So our s will be is equals to our u is 0 times our t, the time taken for the body to accelerate to that point is 20 seconds, plus a half times the acceleration, which is 1, and then the time again, but then this time it is squared. So we shall have it as our distance of a will give us, when you multiply this you get 0, then we shall have 1 over 2 times 1 times, if you have 20 squared, that means you have 20 times 20. What will you get if you multiply this and this? You have 0, multiply 0 times 2, you get 0. You have 2 times 0, you'll have 0 here, then 2 times 2, which will give you 4. So you'll see that you add here, you'll see that you'll get 400. So here becomes 400. So on getting that, we shall have our distance is equals to these two, we can cancel it here by this, which will go here twice. Then if you have 1 times 200, you'll still get as your distance as 200 meters. So we are saying that the body moved this distance, it covered in 20 seconds, it covered a distance of 200 meters. So if it covered 200 meters, now look at this. This is just to move for 20 seconds. What of the distance it covered in 1 minute? What do we have? Let's look at that. So we should try to find for stage B now. If we have your stage B, let's try to summarize and we see. Stage B here, we are saying that the final velocity for the first body becomes the initial velocity for the second phase of the journey. So what is our velocity here? We can get this velocity from this first formulas here, from the first values we got here. So because if you get the final velocity here, we can easily get the initial velocity of the body in the second stage, stage B of its journey. So we can have from V is equals to U plus 80. Our V will give us our U as 0 plus our A is 1 times our time, which is 20 seconds. Our V is equals to 20 meters per second. So we say that this body, when it reaches here, it has a velocity of 20 meters per second. So that means that at this point here, the initial velocity of this body when it reaches stage B becomes the final velocity here. So that means that our U in this case here is 20. And what is our time frame? You get your 80, subtract 20 from it. The value you get there becomes your time taken for the body to move from here up to that point. So that will give us 60 seconds. So if we have that, what do we need again? Do we have the acceleration of the body when it was moving there? Because we are going to use this same value here. We need to know at what rate was the body accelerating. But we know that when the body is moving with a uniform velocity, the acceleration at that point becomes 0. So it is accelerating at a 0 rate. So here we have it as our 0. So to find the distance covered when the body was moving with the uniform velocity, we shall have our S is equals to UT plus a half AT squared. So we have our S is equals to, our U this time is 20, times our time for the body to move is 60, plus a half. Our acceleration at uniform velocity is 0, and then our time is 20 squared. So this 0 cancels the whole of that out. So we shall have our time, our distance is equals to 20 times 60. So 20 times 60, what will you have? If you have 60, then you're multiplying it by 20. You'll have 0 times 0 is 0, 0 times 6 is 0, 2 times 0 is 0, and then 2 times 6, 2 times 6 you get 12. So you add the whole of this, you'll have 0, 0, and then 2, 1. That means that the distance covered when the body was moving with the steady speed was 1,200 meters. So that is still not our total distance. We still have the distance covered by the body, by the cyclist when it was coming to rest. Because here you see that they say that our cyclist was also coming to rest. So how do we get that? So we are having it as let us look at this now, stage C, when the body was coming to rest. With stage C, our initial velocity is equals to 20 still. The time taken for the body to come to rest here is what? If you look at this and this, you get 90, subtract 80 from it, you'll have 10 seconds. So what of the acceleration? What was the rate at which the body was decelerating? So you can get that, because if you get this, you'll have your, to get this deceleration, you can get it from the first equation of motion, which is V is equals to, we can have it as V is equals to U plus AT. We want to get the acceleration there. So we shall have, make our acceleration the subject. Our V here is equal to the U, because at this point the two velocities are the same. So we shall have it as our 20 is equals to 20, then plus our deceleration we are looking for, and the time was 10 seconds. So you'll see that we have 20 is equals to, if you have 20 plus, you'll have 20 plus 10, 8. So we take our 20 this side. What shall we be left with? Let us write it in a bigger space. I think we'll have to grab this question out to see what we shall get there. Okay, now let's look at stage 3. I mean the stage C. At stage C, what is our initial velocity? Well, at this stage here, that means that the final velocity of our stage B becomes the initial velocity of our stage C. So our U at that point is equals to 20 meters per second. So what is our time frame? You get your 10 minus 80. You get your 10 seconds. So look at it again. You need the V, which is your final velocity. So the final velocity the body will attain at this point will become 0, because the body is moving from there and coming back here to the 0 position to rest. So the final velocity when a body comes to rest is 0. So you can see that one here, we shall have it as 0 meters per second. So now, what is the rate at which the body was decelerating? We have to first get the deceleration from our V is equals to U plus AT. Our V this time is 0, and then we have our U, which is 20, plus our A, which is what we want to find, and then the time, the 10 seconds. We have our O is equals to 20 plus 10 plus 10A. Now if you have like that, we want to get the value of A, meaning that we can make it the subject. So we shall have our 10a is equals to negative 20. So that means we have taken 20, we have subtracted 20 from both sides of the equal sign. So if you have it like that, you divide it through by the coefficient of a and divide it by the coefficient of a, which is 10. We shall have our a is equals to 20, negative 20 divided by 10, we shall get negative 2. That means that the body was decelerating at the rate of negative 10 meters per second squared. So we are having this negative because the body is moving in the opposite direction. So now if you have it like that, meaning we can now get the distance under that. So to get the distance, we shall have our s is equals to ut plus a half at squared. Now our distance will be our u, which is 20, times our time, which is 10, and then plus a half our deceleration, which is negative 2, and then our time, which is 10, but then this time it is squared. So when you multiply this, 20 times 10, you get 200, plus this 2 shall cancel with that. So we shall have that one is negative 100. So you'll get s is equals to 200 minus 100. Our distance covered when the body was decelerating was 100 meters, meaning that the total distance moved is equals to a distance covered by a plus distance at stage B and then distance at stage C. So we shall have distance at A we covered was 200 meters, at B we covered 1,200 meters, and then at C we covered 100 meters. So when we add all this, 200 plus 1,200, we shall have 1,400, plus 100, we shall have 1,500. So this is all in meters. That means that the cyclist covered a total distance of 1,500 meters. So you just get the distance under each, you divide your movement, the movement of the cyclist in 2 stages. Then if you get that, you calculate their distances, then add them together. So that is how we find the distance using the equation of motion. So we shall look at other examples to see how we can calculate the distance under a graph using other formulas. Thank you very much for attending. We shall meet again next time.